First of all, I will show where the planner becomes too optimistic. Then I will go through two real cases. The first one is wrong index choice, and the second one is underestimated joins. And after that, I will briefly discuss common fixes and why they are not always enough. And then I will show where and what planner side changes help in these cases. And in the end, I will summarize some practical takeaways. So first of all, what too optimistic means. By too optimistic, I mean that the planner expects much fewer rows than it will actually get. And when it happens, different plans may look almost equally cheap, and the chosen plan can still be correct according to the cost model, but during execution, it does much more work than it was expected. And this is the main pattern behind both examples in this talk. A look at two concrete patterns. The first one is index choice, when the planner has several possible indexes and the path that he chooses leaves too many rows for filtering. And the second one is join estimation, when the planner expects a join to be very small, but in reality, the result is much bigger. In both cases, the root problem is the same. The planner underestimates the amount of work. This matters because many of these queries are generated by applications. So the SQL by itself can be valid, and even the right indexes can already exist. So the problem is not always the query text. So we can see the same pattern often appeared in many times, and it makes manual fixes hard to scale. So in such cases, the real issue is often the planner decision when it has weak estimates. There are actually several standard ways to work with such plans. We can add indexes, but it doesn't help if the planner still chooses another index. And also extended statistics can improve some estimates, but they are harder to apply when we have many columns and many equality conditions. And also planner settings, of course, like disabling join methods. It can be very useful, but it is not a ready production solution, so we need a smaller and more targeted way to improve planner decision in these specific cases. There are broader ways to deal with bad estimates. For example, adaptive query optimization. It can use information from previous execution to improve future plans, and query reoptimization. It can also use runtime information and adjust the plan during execution. Of course, these are powerful ideas, but for cases that I will talk about in this talk, we wanted something smaller. The goal is not to solve all cardinality estimates problem. The goal is to improve a few specific planner decisions when the estimate becomes unreliable. So let's go to the first one. It's about index picking. And let's start with my case from my practice. This is a generated update query. And the important part is not the whole query, but the form of this query. It joins two relations using many equality predicates. And the planner has several possible indexes for the inner side of the join, but because there are many predicates, the estimates become very small and different index paths start to look almost equally good. And in the next slide, we will see what it looks like in the execution plan. So now, at first glance, you may think that this plan look quite reasonable because it uses index scan, but the important part is inside of the index scan. Only part of the predicates is used in the index condition, and the rest, around 18 equality predicates, remain in filter. So the index is executed around 200 times, once for each row from the table, and each time the index returns candidates, and then Postgres checks the remaining predicates in the filter. The K line is row removed by filter. You can see that it's about 80,000. This means the index brought too many candidates, and most of them were removed only after the index access. So the problem is not that the filtering itself happened. The problem is that too much data reached the filter, and this is what makes the plan slow. So let's look at what happened inside the planner. It built several index scan paths, and it uses different indexes. And for each path, only some predicates can be used in index condition. The other predicates stay in filter. In this case, the estimates become very small, so the planner expects only about one row from almost every path. And because of that, costs become very close, and the planner chooses the path that looks quite simply cheaper, but this path leaves too much work for the filter. And this is why we get many rows removed after the index scan. Here we keep the same query shape, but we choose another index. The important difference is in index condition. This index can use many more predicates directly during the index access. So we can see that fewer candidates row reach the filter, and so the filter is still present, but it has much less work to do. And this is why the execution time drops from seconds to milliseconds. And the main improvement is not the join type, but the main improvement is choosing an index that reduces post-filtering. And in this case, adding another index is not working because a better index already exists, and the problem is that the planner doesn't reliably choose it. From the planner's point of view, several indexes paths look very close in cost, and it expects only one row, so the difference between them looks really small. And during execution, the amount of post-filtering is very different, so we need a way to improve index choice when we see such estimates that are weak. Index picking, heuristics help. The idea is simple. When cost is no longer reliable, and we can use some additional signals. We prefer, for example, an index path which moves more predicates to index condition, because it means that the index does more of the filtering. And we also avoid path with a large remaining filter, of course. And also, for non-parameterized scans, unique indexes are also more preferable, so they get higher priority. And the goal is not to replace the whole cost model, but the goal is to make a better choice when the cost model cannot clearly distinguish such paths. So let's go to the simplified view of heuristics. We still start with the basic cost, but when the cost is not enough for choosing safely, we add some extra signals. You can see here add-on, which makes a path less attractive. For example, if we have a long remaining filter, and so on. And on otherwise, you can see bonus that makes a path more attractive. For example, if more predicates go to index condition and fewer rows reach the filter. So the goal is simple, is to reduce expensive post-filtering. And now let's look at a small example. Here we can see 4 columns and 3 of them are correlated, and the query has 4 equality predicates. At first glance, we can see that the index on the first, second, and third columns looks very good, but because these columns are correlated, the second and third one doesn't really narrow the result of the first. This is why the planner may think the index is very selective, while in practice another index is better. And now we can look at the same query with the heuristic enabled. And the selected index is different. It uses the fourth and the first one. And this is important because the fourth is just equal to 1, and it much more selective, specifically in this data. And after the index scan, we already have only 1 candidate row, and the remaining predicates are still checked in the filter, but the filter has almost no work to do. So this is the main idea. If 2 paths look similar by cost, prefer the one that reduces the number of rows reaching the filter. What we get from the index heuristic. First, plan choice becomes more stable, of course, in such situation. And the second one is that the planner can use additional signal from the indexes, and for example, how selective conditions are, and whether the index is unique, and how much work remaining for filtering. And in the practical, in the practice, effect is simple. Fewer rows reach the filter, and it means less post-filtering, less superior work, and in the example we saw as much faster plans. And of course, before moving to the next part, we should discuss some limits. It should be mentioned that it is a narrow improvement. It is used only when the planner can't see and can choose safely only one plan. And this is not a full replacement for selectivity estimation. It's empirical rule for a specific uncertain case. And also, as was mentioned above, parameterized paths are also more difficult because the same index lookup may be repeated many more times in a join. So also outside these cases, the normal planner logic is still used. So let's move to the second part. It's about underestimated joins. And in this slide, we can see another generated query. And this time, it has many equality predicates in the join on clause. The planner estimates the join result in only about 1 row, but actually, that's why for it, nested loop looks good enough. But when we go to the execution, the join produces almost 3 million rows. So the inner index scan also executed more than 33,000 times, and 1 for each row. This is the key symptom here. The join looked tiny to the planner, but it was large in reality, and as a result, the selected join strategy became very expensive. To check that the problem was actually in the join strategy, we can just compare alternative plans for the same query. The basic query was with nested loop, and it was executed in more than 1 million milliseconds. And if we disable nested loop, then the planner chooses merge join. And this time, the query becomes much faster. And the second, if we also disable merge join, then the planner, of course, chooses has join, and we can see that the time drops even more. So this doesn't mean that has join is always better. It means that in this specific case, the original cardinality estimate was wrong, and the choosing join was that's why became the main source of the runtime. So let's discuss why does it happen. With many equality predicates, the planner has to estimate how selective the whole join condition is. And a common problem is that selectivities are multiplied. And the final estimate becomes very small because of this. And in real schemas, predicates are often correlated, and the planner may assume more independence than the data really has. And also, we often don't have statistics for large combinations of the columns, like in previous example. And as a result, the estimated number of rows becomes too small, and the planner strategies like nested loop or merge join may look cheaper than they really are. So let's discuss when nested loop becomes risky. Actually, nested loop is not a bad strategy by itself. It works well, but when the outer side is small and the inner side can be accessed quickly, for example, through an index. And the problem starts when the planner underestimates the join, and it expects only a few outer rows, but during execution there are many more. Then the inner scan is repeated again and again, and this is why when we'll see loops, it is important signal is in the explain. And if the estimate is small, but the inner node has many loops, the runtime can grow much faster than the planner expected. So this is where join underestimation shielding comes in. Our idea is simple. If a join has too many relevant clauses, the cardinality estimate becomes less reliable. In this case, we move the planner away from the risky strategies, and the trigger is the number of join clauses. If it is above of configured limited, nested loop and merge join become less preferable, and the planner is guided toward to hash join. The SQL query, I need to mention, doesn't change, and the indexes also don't change. We only change the planner decision in this specific uncertain case. So the rule is based on the number of the relevant clauses in a join. We check each join node separately, and if the number of clauses is higher than the limit, the planner is guided toward to hash join, and we don't count only on clause. Relevant filters and filters in outer joins may also increase this uncertainty. So we also consider them. And also, of course, hash join itself must be available, because if it disabled, the planner cannot choose it. And it also has some exception. For example, we check each join. For example, if hash join is disabled, we doesn't change it, and also has join, don't count only another important, and also if the inner side of the nested loop can be accessed quickly, then we also don't change it. And so the idea is simple. We don't force has join everywhere, but when the estimates are risky and join has many relevant clauses. Let's look at the example to understand what I mean. And here we can see that the limit is set to 2. And in the first query, the join has 2 equality clause. And now the join is, and now we choose nested loop because the limit is not exceeded. And in the second query, we add one more equality clause, and now the join has 3 clauses, which is above of the limit. And in this case, shielding is applied, and the planner chooses has join. And also, I need to mention that this example is intentionally simple. We don't have any extra predicates because such predicates can reduce the number of the clauses through equivalent classes. So in such cases, when the planner reduce it through equivalent classes, the limit also doesn't exceed it. And now let's move to what shielding changes and to what it is not change. We need to mention that it helps to avoid risky nested loop and merge join choices when it actually execution appears to be much slower than we expected, and also it makes join strategy more stable when the planner can distinguish different ones, and the most important, it reduces worst cases execution plans for many clause joins, as it was mentioned above in the example from my practice. And also, it intentionally doesn't replace statistics or AQ or reoptimization, and it doesn't has really guarantee that has join is always optimum, because there can be some cases, of course, when nested loop would be better, but it also doesn't fix cardinality estimates themselves. And to control it, you need to has only one parameter, is the limit. Let's move to some takeaways. And some bad plans come from overly optimistic estimates, not from bad SQL. And they happen because the planner underestimates the amount of work, and in the first cases, we can see that it leads to the wrong index choice, and in the second case, it leads to a risky join strategy. And the main point of this talk is that just small planner changes can make these choices more stable without any rewriting application queries. And here you can see developers of the extension when these solutions were developed. And that's all for me. Thank you so much, and I'm looking forward for your question.
And my question is, so I think I missed something. So you have like with Postgre Pro is like your company and you are creating like on top of the Postgre open source your own product and you change the planner.
Yeah.
Okay, because okay, and my question: so you fully replace the planner, or you added like using with planner hooks and etc. And can we, let's say, what you did? Like, is it available to plug, let's say, your optimization or your improvements to the community version via extension and etc. and to use what you did and to to have benefits?
Yeah, thank you for your question. This is extension and it uses Gooks to activate, and actually specifically this extension needs some core patches we also provided, and you can just load the library and start to using it. And also we have another extension that doesn't need any changes in core planner. It just can be used as it is also through Gooks and load.
And can you share the links with the organizer? Like,
yes, of course.
Or put in your slides and it
Yeah.
Thanks a lot.
Thank you.
There's a question I've thought of. The problem you're trying to solve is something I've thought about a lot. Because right now, we just look at costs, and whatever's lower, we pick. And what we don't consider is how sensitive that plan is to misestimates. So imagine you have 1.0 and 1.1. You're going to choose the 1.0, but the 1.0 plan may be very sensitive to misestimates. The 1.1 plan might be might be a hash joint, it may be very immune to misestimates. And it just feels like we don't have a way of codifying, and that's what you're trying to do here, is to get some rules around, if these are really close, how do I get the sensitivity of misestimation within that? I was just wondering, did you try just adding a certain percentage to every cost based on how sensitive or insensitive it is to misestimation?
Yes, actually we tried, but in real world cases it so depends on the query, so it doesn't have any general solution because of it. And yes, and also I should mention that in the newest version in 19, some of the problem in underestimation shielding was already solved, but actually our clients, most of them uses at least in the best only 16 version, so that's why this solution is still working for them. But yes, the community solves some problems.
Probably because of the way we choose indexes is more sophisticated in 19.
Yeah.
That's very interesting. Good to hear. Thank you.
Thank you.
Thanks for the presentation. So I had a question about, like, if there is an extension providing a custom index with its own cost estimate, so do you handle the cases like your planner hooks does pick, like choose the extensions custom cost estimates? Does it work with the extensions?
Can you please repeat the
Yeah, for example, in case of PG vector, it provides the new index for the vector type, right? And it has its own cost estimation because it runs HNSW algorithm. So your planner can take the cost estimation from third-party extensions, the hooks.
It's a good question. I think that